Okay, thanks a lot. So, uh, we'll continue the first lecture, this part 3. We'll maybe have a little bit of discussion before that. So, this old statement by Einstein could be taken as, if you like, a support for trace dynamics. Let's read it. There's no doubt that quantum mechanics has seized hold of a beautiful element of truth, and that it will be a touchstone for a future theoretical basis, in that it must be deducible as a limiting case from that basis. Very nice. Just as electrostatics is deducible from the Maxwell equations of the electromagnetic field, or as thermodynamics is deducible from statistical mechanics. I do not believe that quantum mechanics will be the starting point in the search for this basis. Okay, trace dynamics. Just as one cannot arrive at the foundations of mechanics from thermodynamics or statistical mechanics. So, depends on your outlook. So, maybe we could have had this discussion yesterday, but I wanted to give you a flavor of the theory. And we could ask in the spirit of Einstein. I mean, he did not elaborate why he's saying that. So maybe some of these things is what he might had in mind. So these are possible motivations for believing that quantum mechanics is incomplete. This is a very subjective viewpoint. This is obviously not a proof or a proof that hence trace dynamics, but good points. One is what you could look at historical precedent, that theories which are good and very successful even for a century or two need not stay forever. That has never happened. You know, you look back at the history of physics, nothing is permanent. Newtonian mechanics and Newtonian gravitation was replaced because of Michelson-Morley experiment and other Maxwell electrodynamics. It was replaced by special relativity, by Einstein general relativity. Then we had to give away classical predictability because of experiments like blackbody radiation and discrete spectral lights, and quantum theory came in. Of course, the current interesting situation is there's no experiment that compels us to give up quantum theory. So in that sense, these precedents are of a different nature than what one might say about trying to generalize quantum theory. But the message is definitely there that a theory which is valid in one regime or in one part of the parameter space need not survive elsewhere. So, for example, in the quantum to classical transition, because we see problems like measurement problem, there is no reason to think that we must solve it with quantum theory. Of course, it might work. That's why we have these different foundational interpretations, which Justin discussed. On the other hand, there is a logical possibility that the theory is approximate and not exact. Okay. And the other motivation, this we have heard many times from Dustin, from Angelo, the quantum measurement problem. Maybe quantum theory is not meant to solve this problem. Maybe there's a more universal dynamics, like Angelo introduced, to which quantum theory is a very good approximation at microscopic scales. And trace dynamics is one such example of universal dynamics. Then the origin of canonical quantization rules. Where do these rules come from? You remember, we have to start from a classical theory. We should know the Poisson brackets for the dynamical variables. And we are told, please go and replace those Poisson brackets by commutators. That's what you might call a recipe or an algorithm, but not fundamentally satisfying, because you have to know the classical theory before its parents. You know, it's like the son is being born before the father, kind of thing, whatever, daughter. So can we derive the canonical quantization, commutation, and anti-commutation rules rather than imposing them as a recipe on the classical limit of the theory. Then infinities in quantum field theory, do they suggest that we need to do something to the theory? Non-locality also we have discussed quite a bit. Does unification of quantum theory with gravitation, maybe because of all the difficulties that are faced, it calls for relook at quantum theory. And for me, the cosmological constant problem is a very strong indicator that something is wrong. Quantum theory says there's a very large zero-point energy in the universe, and if all energy gravitates, we should have seen its effect, and if its effect had been seen, we won't be there, because it's so high that the universe won't last more than one Planck time. The fact that we are around means that this energy does not gravitate. So that violates general relativity, and something has to give. The GR doesn't apply to quantum theory, or quantum theory doesn't apply to GR, but they both don't apply to each other. And that's, for me, a part of this question. How well do we understand quantum theory? It's, I think, an extremely deep problem, deeper than many of the others, because something that should happen is not happening. So maybe you want to discuss this, you want to add to this list, or subtract from it? Okay, so. Dark matter, does it require us to modify quantum theory? I don't know. But as a mathematical formalism, you need the commutation rules, isn't it? You could say that the uncertainty principle comes from the commutation relation. Not quite the other way around, no? Commutation relations and the Schrodinger equation together. That is a good point. But how do you make a mathematical formalism out of it? You have to know the classical dynamical variables. You have to know the classical Lagrangian and Hamiltonian. You have to know the classical Poisson brackets. And then the mathematical recipes replace Poisson brackets by commutative. I don't know if just knowing the uncertainty principle, for example, you may know the uncertainty principle, but you won't know what the classical Lagrangian is, right? Yeah, I think that's a good point. To what extent it leads you to the full mathematical formalism for going from classical to quantum, let's think more about that. Yeah. So you want to discretize space-time, or Yeah, so you are right. One cannot pinpoint that this problem is arising. We cannot say that this problem is arising because quantum theory is incomplete. That could be one of the reasons. Mhm. Yeah, but like I think who Dustin was talking, I mean, what is happening in quantum field theory? You have a somewhat ad hoc procedure of renormalization, what Dirac also. I agree, but that doesn't solve this problem, no? No, I didn't say that. I didn't say it's wrong. But suppose a modified theory provides you a natural cutoff, like string theory is supposed to do that. That would be more satisfying than having a infinity, no? Not wrong, but approximate. That's what I mean. Not wrong. Quantum theory is not wrong. Okay. Then the problem of oh, yeah, sorry, I think we went through this. We can talk more. Okay, so we go on. All right. So I thought I'll briefly, just quickly run through the slides of yesterday because I did get a feedback that this stuff is a little bit over the top, it's too formal, and also I have not shown any derivations. So let's just, and if you have any questions, you can ask as we go along. Such as there are 3 steps. Step 1 is the classical dynamics of, so I should say one thing. So this is the motivation, let's say, for considering the possibility that QM is incomplete. When we are done with the part 3 of the talk, we'll come back and do a reality check. Did trace dynamics solve any of this? So we will have a critical look at that. Okay, so step 1, classical dynamics of random non-commuting matrices. And there is a very important conserved charge, the Adler-Miller charge, or remember this symbol C tilde, which is used all the time. Okay, and let's also recall. So step 2 was doing the thermodynamics, the statistical mechanics and thermodynamics of this underlying classical microscopic theory of matrices, which as a consequence of a certain invariance in phase space, which is the analog of equipartition theorem, led to the averaged quantities obeying Heisenberg equations of motion and equivalently the Schrodinger equation. I'll comment a little more on that. And part 3, what we want to talk about today, is that around equilibrium there are fluctuations. One example is the Brownian motion type of fluctuations, which we will see lead to a modification of quantum theory to a nonlinear stochastic Schrodinger equation of the kind that Angelo is talking about. And that is a possible solution for the measurement problem and for the derivation of the bond probability rule. So in a spirit, the spirit is that trace dynamics is one possible fundamental explanation for collapse models because of these ever-present statistical fluctuations. So just go through these slides quickly. Definition of Grassmann variables, bosonic sector, fermionic sector. So stop me anytime you want, if you have any questions from yesterday. So matrices can be decomposed into bosonic type or fermionic type. The definition of the trace in the standard way. In the definition of the trace derivative, we didn't use it in the calculations, but it's implicit Whenever you see a derivative with respect to an operator, it is a trace derivative. Then the definition, the introduction of the classical dynamics of these matrices, which is a standard formalism, except that now we are dealing with operators QR and PR. And I should mention that's another motivation for Adler to avoid coming from classical to quantum by replacing Poisson brackets by these commutations between operators. Why don't we start with the classical dynamics of operators so that you don't have to by hand, by recipe, replace C numbers by operators. You start with operators and see what you can do. Okay, so we had a trace Lagrangian, trace Hamiltonian. We wrote down Lagrange equations of motion, Hamilton's equations. Given is bold A and bold B, which are traces of polynomials, we can define a Poisson bracket. It obeys the Jacobi identity, and the equation of motion, which is analogous to the equation in classical mechanics. Okay, then there were three conserved quantities: the trace Hamiltonian, the trace fermion number defined like this, and the most important is this C tilde, which has the structure of commutators for bosons minus the anti-commutator for fermions. It has the dimensions of action, and as you saw, most of the story is about this conserved charge. It is also in Poincare invariant, it's anti-self-adjoint, and it is traceless. Okay, we can define in a standard way a measure on the phase space the way and Liouville's theorem holds. Okay, then to the thermodynamics, define a probability density in phase space for these phase space variables XR, which is QR or PR. At equilibrium, the density function rho, phase space density rho should be a constant. Rho dot is 0. Okay. Now is when things start getting non-trivial. The density, the phase space density depends on these constants C tilde, trace Hamiltonian, and the trace fermion number. It depends on corresponding Lagrange multipliers, lambda tilde, which is an anti-self-adjoint operator, tau, which is the analog of temperature in ordinary stat mech, and eta, which is the Lagrange multiplier corresponding to n. And lambda and tilde and C tilde enter the space density in this particular combination, trace lambda C. All right. This is one of the most important slides. Maybe it got caused some confusion. So this O average is the phase space average, the canonical ensemble average of an operator O, when defined in the standard way. And since lambda tilde is the only operator, this average of this operator O can only depend on lambda tilde, and hence this average commutes with lambda tilde. In particular, if you take O to be the Adler-Millard charge, then one can prove, I did not give you that proof, that this C tilde average as a consequence of this commutation relation can be written as a product of two matrices, I effective and D effective, whose trace is 0, and I effective satisfies these properties. It commutes with D, and importantly, D is a real diagonal and non-negative matrix. Okay, so all the elements would be positive, and we made this very important assumption, which we would need further proof in the future, that all the diagonal elements are equal, which means no state is favored over any other state, which allows us to write this C tilde average as this I effective times the constant, which we denote as h bar. And for consequences that follow, we identify this h bar with Planck's constant. Okay. Then we can construct the equilibrium distribution by maximizing the entropy. Subject to these constraints, the probability is, total probability is 1. C tilde is conserved, H is conserved, N is conserved. And this is pretty standard. You maximize this entropy subject to these constraints by multiplying them with Lagrange multipliers. And you find this partition function given in the last line. And the equilibrium density function is defined in the second last line. So here is where I can mention that you can also add source terms if you want to derive some canonical averages. A term like plus JR XR vary with respect to XR and in the end set J to 0. Okay. So how did quantum field dynamics emerge? In analogy to the equipartition theorem, we looked at variations, constant shifts in the phase space, XR going to XR plus delta XR, and demand, not demand, it should be, it's a natural thing to happen in the theory that averages like rho times O, forget that J for the moment, those averages should not change under these constant phase shifts. And now consider the operator O defined in this following way, where W is a polynomial. And for this particular operator O, find out the variation of this quantity. Actually, the trace is there. I was confused about it yesterday. Instead of O, we have taken trace of O, and that's the quantity which has been varied. The trace is correctly there. Okay. So all we have to do is vary this quantity after including sources. It's a very long calculation. It goes over a few pages. But subject to these three assumptions which I mentioned yesterday, most important of which is that C tilde average will be replaced, C tilde will be replaced by its average I times H bar in what follows. And in the third part of the talk, we are going to modify assumption number 3. We'll stick to 1 and 2, but we'll modify assumption 3 to say C tilde is equal to its average plus a fluctuating quantity. And we'll see what that does interesting things. So those are the fluctuations which we want to take into account today. Okay. So when you do this variation here and lead it to the end, you get this first equation, namely the canonical average of this operator D acting on a phase variable X is 0, where D is defined like this. It is I times the commutator of W with X minus H bar times the trace derivative of the trace of the polynomial W. If we took W equals H, we got Heisenberg equations of motion. If we took W equal to the phase space variable, we got the commutation relation. Okay? So it is in this average sense that one recovers quantum dynamics from the underlying trace dynamics. And then we talked about how one can map these canonical averages to actual operators in quantum field theory. So this gives us the Heisenberg equations of motion in quantum theory, in quantum field theory. And this last point I should emphasize, it was asked by someone later. How do I get the wave function out? How do I get the Schrodinger equation out? That is done in the standard way that we do, say, in our college textbooks, going over from the Heisenberg picture to the Schrodinger picture. So after we have got the Heisenberg equations of motion, we can forget trace time. If we have ordinary quantum theory, then in the Heisenberg picture, the wave function is a constant, operators evolve. We know how to make a transition to the Schrodinger picture, where the state evolves, but the operators are constants, and you can get the non-relativistic Schrodinger picture out in usually. So that I'll take as a given. I won't go through it. Let's say we have the non-relativistic Schrodinger equation at equilibrium when we replace C tilde by its average IH bar. Okay. So now we come to today's talk. The equations here are, in a sense, even longer, so I'll just give you a flavor of what's happening. We cannot, I mean, of course, you won't derive those equations. Some of them are pretty long, but I hope you'll get a feel of what went in. Okay. So first point I've already talked about. In deriving the Schrodinger equation, we have made certain approximations valid at equilibrium. We replace C tilde by its canonical average. And now we want to consider fluctuations about the average quantities to see what that does to the Schrodinger equation. So this is, I think, one of the most important messages of trace dynamics. It has within it, in a very natural way, the germ for stochasticity that Angelo introduced. Like when he talked about the GRW model, one of you asked him, why? Where did you get this from? So in the GRW model, it's an assumption which is motivated by the desire to solve the measurement problem. The motivation is phenomenological. You know which problem to solve, so you introduce GRW. Here you are not trying to solve a problem. Adler's claim is, even if you did not want to solve the measurement problem, you'll end up solving it because there are always thermal fluctuations about the equilibrium. You know, for example, Brownian motion fluctuations are supposed to explain the blue of the sky. So there are very many situations where fluctuations around equilibrium are important, and this is claimed to be now one such situation. Okay, any questions? All right. So now is, as I said, I'll be jumping a lot of steps. I'll take some time on this slide, go slowly. So let's first write down the fluctuations of this conserved charge C tilde about its average. Okay, so let's see, delta C tilde is a fluctuation, C tilde minus average, C tilde minus I effective times H bar. And I define these two quantities, kappa and n, as a descriptor of those fluctuations. Kappa is a C number fluctuation, n is a matrix fluctuation. I mean, because kappa times identity, you can think of it like that. So that's just a natural way to decompose the fluctuation, that there is a sort of non-matrix part and there is a matrix part. So then again there's a very detailed calculation that if you replace C tilde by its average, you got the Schrodinger equation. If to those averages you added these stochastic quantities kappa and n, what will you get instead of the Schrodinger equation? And the result is shown in this equation for phi dot. We need to dwell on it a bit. So let's see. You can identify the Schrodinger equation part, this h multiplied by this minus IH bar, okay, that the Schrodinger equation. Rest is all new because this kappa and m are new terms. That is the stochastic modification of the Schrodinger equation. But we must note right now that this is a linear equation. So stochastic linear Schrodinger equation. We want nonlinearity. We'll come to that, like Angelo said. To solve the measurement problem, you need stochasticity and nonlinearity. So stochasticity has come, okay? But it has come because of these fluctuations, but it is linear. So we have to think some more. This kappa has been decomposed into its real and imaginary parts, kappa 0 and kappa 1. Similarly, this matrix N has been decomposed into real and imaginary parts. Okay. Kappa is a C number, N is a matrix. Kappa times identity matrix. Right. Okay. So let's go slowly. Just look at the Schrodinger equation again. Some new important fellow has come up. You see, you have on the right hand side, the first term IH bar times the Hamiltonian. That is the unitary evolution, and seems natural because in a way you can combine the two and you can write it like one matrix. I don't know what are the other possibilities. Okay. So the first term, my IH inverse times Hamiltonian, that's unitary evolution. But notice now that there is an imaginary part to kappa. So it's I kappa 1. If you multiply it with another I, it becomes real. So you have a non-Hermitian contribution to the total, to the corrected Hamiltonian, which would make the evolution non-unitary. Okay? Which also something which you need if you are going to want to cause collapse. And this is how you bring that feature in. Okay? Same for this last term, M0 plus IM1. So this is actually a matrix decomposition. I think I should, I just maybe lost one step. This is the assumed Hamiltonian. So let me make a few remarks. This is the assumed Hamiltonian for writing down this equation. The Hamiltonian could have been anything, but we are dealing with the non-relativistic matter because we want to understand measuring apparatus interacting, let's say, with the ordinary non-relativistic quantum system. So only fermions are retained. So I will not go into how this structure for the Hamiltonian has been written, except to say that MR is a mass species. There are different particles with different masses. MR is the mass for the Rth species. And this expansion is over an entire set of basis states, some complete basis, basis of states. Okay, that is how this summation comes about, and this choice of the Hamiltonian would lead to the corresponding Schrodinger equation. N also is decomposed into real and imaginary parts. Okay, and so N0 would be the real part of N. N1 would be the imaginary adjoint and anti-self adjoint parts, each of which is this is gone. Right. N is written as a N0 plus N1, and this matrix M is defined from a given N like this, and it is split into its real and imaginary parts, or adjoint and anti-self-adjoint parts, which are shown in the Schrodinger equation. Okay, so I hope It's the same thing. The n in the top line is first written as n equals sigma r n r l and split into real and imaginary parts n0 rl and n1 rl. Okay? And you write a m, which is defined in the last equation, and you split it into its real and imaginary parts m0 and m1. I missed a step, I'm sorry. You get the picture? Yes, that's correct. Okay, so I hope you get some feel. Basic step is very simple. If you modify, if you replace C tilde by average plus fluctuations, you are going to add fluctuating modifications to the Schrodinger equation, which are represented in this form. This is now a stochastic term. The theory does not say what should be the nature of these fluctuations. Should it be white noise, should it be colored noise, or something else? So now we have to start making some assumptions. Essentially what this leads to now is a very wide class of stochastic Schrodinger equations. The theory doesn't predict the GRW model, but that model will be contained in this as a special case. We'll see how. Okay. So the simplest case to deal with is white noise, or let's say, also you can think of it as Brownian motion, described by this stochastic function W, okay, also known as the Wiener process. And we are going to assume that we will write this kappa and n in terms of this Brownian motion kind of stochastic process or white noise. That's one model. That's the model we are going to work with. And these last three equations on the right define what is known as a Ito calculus. If you have stochastic functions, which are random functions which take random values according to some probability distribution, they have this property that dw square is proportional to dt, dwn times dwm vanishes if m and n are different, and the last line shows that the product of dw and dt is 0 and dt square is also 0. So this, I don't know if you're familiar with stochastic calculus, otherwise you can take up a book. Gardiner's book is very nice, book on stochastic methods for physicists and engineers, which will discuss Ito calculus and the stochastic differential equation. Okay, so what we want to do now is write down these fluctuations in terms of these Wiener processes. Our first two equations define the C number fluctuations, and for the matrix fluctuations, we also assume that they have spatial dependence that we are going to need to get to the collapse model if you want to recover the collapse model from here. Okay, and for each of these Wiener processes, there is that Ito calculus which it has to obey. So introduce these new constants, beta I, beta R, new matrices, Mi, X, and MRX. Substitute these definitions in this Schrodinger equation, which is linear. You still get a linear equation. Sometimes I make a mistake. I write a H effective. Just ignore this. It's always H. This is a typo. And this is the most general linear stochastic Schrodinger equation for this Brownian motion type of processes that we are going to get from trace time. So the first term is the Schrodinger term. Then there's the term, there are two terms, beta I and beta R, coming from the C number fluctuations. And notice one has a imaginary factor, one doesn't. And then the last two terms are coming from the matrix fluctuation. Okay. What do we want to do next? We want a nonlinear stochastic Schrodinger equation. There's no way to get out of this. Then comes what, in my opinion, is probably the weakest link in this project. What you can show is that the moment you add these linear fluctuation terms, you get an equation which does not preserve norm. Now one could ask, what's the problem? It's okay, let it not preserve norm. Norm preserving is not not a sacred principle, except that in non-relativistic quantum mechanics, it is related to particle number conservation. We know from experiments that the particle number is conserved in the non-relativistic theory, and that is proportional to the norm. So we will run into trouble with experiments if we don't impose norm preservation. Now, I think the correct stand to take is the theory should not have to depend on the experiment to know what form it should take. Norm preservation should be predicted. Namely, you should have naturally arrived at fluctuations which are such that when you add them, norm continues to be preserved. That does not happen. So in that sense, it's a shortcoming which needs to be taken care of sometime. You're saying if they are linear, we are going to get a stochastic norm-preserving Schrodinger equation, but it will be non-linear. Now, sir, this is not norm-preserving. I don't want to make a general statement. The are you asking, can I have a linear stochastic Schrodinger equation which is norm-preserving? I don't know the answer. I don't know if Angelo does. He's busy. Can I ask you? You have a linear stochastic modification of the Schrodinger equation. Is it always true that it violates norm preservation? It won't preserve norm. Yeah, that's what I'm saying. Yeah, yeah. This is not unitary. Oh. Yeah, I think that's a good point which I overlooked. It's linear but not unitary. That's responsible. Right. So now we, okay. So now we impose norm preservation by hand. As I said, theory should ultimately one day do better. But we define a new state psi, which is phi divided by its norm. So clearly, obviously, psi will be norm preserving just by construction. So go back to this Schrodinger equation written at the bottom and make the transformation from phi to psi. Then you arrive at this very long nonlinear stochastic Schrodinger equation which preserves norm despite being not unit. Okay, so now let's spend some time at it. How did we write this equation? So in arriving at it, two assumptions have gone in. One is norm preservation. The other is the criterion of no superluminous signaling. Comment on that in a moment, which we just heard a lot about today morning in Angelo's talk. What you do is that once you make this transformation from phi to psi, you write down the full Schrodinger equation for psi. You construct the density matrix operator for it. Look at the stochastic average for that density matrix operator. And look at the structure of that equation. The density matrix obeys a nonlinear equation, which you don't want for reasons that you heard. That equation better be linear, otherwise you will have signaling. You saw that in detail here. If you make that equation linear, you have to set certain terms to, question? You have to set certain terms to 0, which if you do that, this is the equation you land on. This equation, so I keep emphasizing this point that one is not happy with imposing norm preservation by hand. Because in a sense, then the Born rule is built into the model. Although I will claim to derive the Born rule in the end, it hinges on this assumption of norm preservation. Okay? All right. So you can look at a bit at the structure of this equation. I don't think I want to read it out in full. What is important is if you look at the last term, okay, you have you have terms. These are expectation values. You have terms like h minus h average whole square times dt, and you have terms like h minus h average into dw. So something which is multiplied by the stochastic process, its square with a minus half is multiplied by the square. So h minus h average here, h minus h average square here, here a plus beta, here a plus beta r, here a minus half beta r. So this structure is very central. So if you have some operator A, you have A minus A average times dW multiplied by a constant minus half square of the same constant, A minus A average whole square. You will, I think, see this now in Angelo's talk. This is known as a so-called martingale structure, which is what is responsible for the Born rule. The collapse of the wave function will come from stochasticity. The Born rule is dependent on this so-called martingale structure. And if you go back, and if you don't know about this already, something known as the gambler's ruin problem. Okay, and, I mean, let me not go into it right now. You can Google it. It's a very interesting situation. Two gamblers, one has more money, one has less. I think the one who has less money always loses in the end. And that actually was the motivation for this construction of this particular so-called martingale structure of collapse models. Phil Pearl was the first person to do that, 1976. I think mentioned his work. So that even before GRW, there were stochastic nonlinear Schrodinger equations around to solve the collapse problem. So first model is actually Phil Pearl, 1976. Okay. So the claim is this general structure, which has come on the basis of two assumptions: no signaling and norm preservation. It turns out that if you are dealing with white noise, you have got this Schrodinger equation, and if you impose these two conditions, norm and no signaling, you will get at this equation, and you cannot have higher order terms because of the Ito calculus. You see, it is the structure, dw square is 0, dt square is 0. There will be no more terms. So, for white noise and norm preserved and no signaling, this is the most general stochastic nonlinear Schrodinger equation that you can get. And collapse models in particular are contained in it as a special case. So the theory does not predict GRW or CSL model uniquely, but contains it as a special case. And this, I think, you will see in Angelo's talk. You will see this equation, which is the sort of differential equation formulation of the GRW model. The first term is the unitary Schrodinger evolution. Then just compare the structure of the second and third term. As I said, one of them has a coefficient root gamma times m naught. The other has a coefficient which is minus half the square of that coefficient. And this second and third term are contained in this general equation. And you can arrive at this GRW or CSL model from the trace dynamics equation, provided you choose your MR in the following way, where if you look at the right-hand side, G is a sharply peaked Gaussian function, which you saw in Angelo's talk, and NR is the number operator for the rth degree of freedom at the location Y. Okay, so this is a bit preempting what will come in the next talk. You will see this model there, and that model is contained in this Adler equation as a special case. So in that sense, subject to these assumptions, the phenomenological model of GRW is derived from this fundamental theory by taking into account these fluctuations. So in that sense, fluctuations are very important, and quite natural that the equilibrium theory is a deterministic theory, quantum theory, and the fluctuating theory is a probabilistic theory. So now we go and do the final rituals. Get out of this collapse of the wave function and the bond group. Okay, and then we will look at what the theory achieved, what remains to be done, and we can have some discussion. Okay, so to explain collapse of the wave function, we consider, we don't want to work with this whole mess, we don't need it. We consider simplified version where you want to look at the collapse of some operator, some observable A that is being measured, a set of eigenstates, and we want to show how the unitary evolution of the Schrodinger equation is destroyed by these this martingale structure. So what do we have? We have the Schrodinger term. We have this is what the important structure that I talked about, minus half here and the square of that here, okay, and these are some other terms which are from the most general Schrodinger equation. Okay, so what do we want to do with this? We want to show that if you make a measurement and the initial state is a superposition of eigenstates of A, and you make a measurement, there's going to be a collapse to one of them. That's what's called dynamical collapse. You will see this, I think, in a different way in Angelo's talk, a different derivation of the same thing. So we write down the corresponding density matrix for this stochastic equation that is shown in the second equation. Again, not H effective, H. Okay. Let's define by these E brackets expectation value of some quantity with respect to this stochastic process W. So there are two kinds of averages. Quantum expectation values, they're shown by a wedge. Like in the top line, A wedge is the quantum expectation value of A. E bracket something, E bracket A, let's say, would be the stochastic average of some quantity. All right. Now this is a proof in a few lines of how collapse takes place. We define this variance of A as done here. A minus expectation value of A whole square and the expectation value of that whole quantity, quantum expectation value that we call the variance of A. All right? Okay. So that can be written in terms of the density operator as shown on the right-hand side of the first equation. Okay. And now I want to prove that as time goes to infinity, as a result of this stochastic process, this variance goes to 0. The only way the variance can go to 0 is if A goes to one of the eigenstates and if the superposition is broken. Okay? So how to see that? Look at the second line. It can be shown from the definition of V using the master equation for the density matrix that a time variation of E satisfies this equation dE of V, where E is the stochastic average, that is equal to this quantity on the right hand side. That is how E evolves with time. That's the second equation. You integrate it, okay, integrate that differential, you get the third equation, which shows the time evolution of E of V, the stochastic average of V. That's the third equation. Now I want to rewrite that third equation as this equation number 5, the fifth equation in the row, using inequality. So I'm going to replace E of V square by square of E of V using this inequality, which is quite obvious because what you have in the fourth equation, V minus E of V whole square is a positive quantity, so stochastic average will be non-negative, and the right-hand side here is just open this up, yeah, that is what this is. So as a result of this result of the positivity of this object, okay, you can write down this equation number 5 from equation number 3. That is, I've converted 3 to a inequality. Okay. Now let's look at equation number 5. The right-hand side, the second term, is a negative minus of an integral of a positive quantity. So as clearly as t goes to infinity, the integral is going to rise, but the left-hand side is non-negative, and the only thing that this is going to lead to eventually is that E, the stochastic average of V at time infinity, must be 0. It's the only way to satisfy this in the limit t goes to infinity. And V of t is a positive quantity. If the stochastic average is 0, it clearly has to by itself go to 0. So this is one demonstration Notice that all this is coming because of this particular Schrodinger equation and master equation. The properties of these equations won't be true in general. The second equation is the consequence of applying the master equation to this definition of the variance. So because the variance goes to 0 at infinity, the system is driven to one of the eigenstates, and that is collapse. Of course, we don't know which one. That happens randomly. The theory is not supposed to predict which one. But it should give you the Born rule that will come to in a moment. And the last equation can be derived from equation number 5 simply by first differentiating with respect to time and then integrating that equation. That will give you this upper bound on E of V of t, which essentially gives you a reduction rate. If you look at the denominator on the right-hand side of the last equation, that gives you a time scale which is 1 over beta r square V0. That will define the rate of collapse. So that can also be worked out once you know your stochastic. Okay? Okay. So now the last calculation, then we'll do a reality check. Okay. How to derive the Born probability rule? Okay. Namely, that this collapse, A has collapsed to some eigenstate, and the probability should be given by the Born rule, which is the following. That so first, let's define this projection operator pi A, which projects onto the ath eigenstate of A. If the initial state is the superposition state when you start just before the measurement process, psi I is sum over the space states A with the amplitudes Pia, and we know that the Born rule is that the ath state should be realized with a probability mod Pia square. We know that collapse has taken place. The stochasticity predicts collapse. We want the right probabilities. Okay, this is the state at t equal to 0 before the stochastic evolution sets in. Now let's look at this quantity E pi A expectation value. Where is it? Yeah, at t equal to 0. There is no stochasticity happening at t equal to 0. So the stochastic average is the quantity itself, this pi A at t equal to 0, which you can read off easily, nothing but mod Pia square. Yeah? That is the stochastic average of expectation value of pi A at the beginning. Now, we have shown that eventually the system results in a particular eigenstate f. Let's say with some probability Pf, we want to prove that Pf is mod Pia square. Yeah, that's what we want to prove. Okay. So if it goes to the fth state with a probability P, then it follows that the following is true. Let's see. The stochastic average of pi A expectation value as t goes to infinity is obviously nothing but this sum. Yeah, because it goes to mixed state now. The battery is dying down perhaps. So this sum on the right-hand side is what is the stochastic average of the projection operator's expectation value. The probability Pf that it goes to the fth state multiplied by the expectation value of pi A in the state f summed over all states, which you can clearly see if the states are orthogonal, that is nothing but PA. You get that? The stochastic average of the pi A expectation value as t goes to infinity is PA, which is nothing but the probability to go to the ath state. Now, this is next is an interesting result that if G is an operator which commutes both with H and if G is an operator which commutes both with H and A, then its stochastic average of its expectation value does not evolve with time. That is this second last equation, stochastic average of D wedge G. Okay? So now the projection operator commutes both with the Hamiltonian because A commutes with the Hamiltonian and the projection operator commutes with A also. So if I take G equals A, that tells me, sorry, if I take G equal to the projection operator, it tells me that the stochastic average of the projection operator does not change with time. So now we are done. The stochastic average of this expectation value of pi a at t equal to 0 was mod pi a square, and the stochastic average of this expectation value as t goes to infinity is the probability to be the ath state Pa, and hence it follows that Pa should be the square of the m. Do you get a hang of it? Okay. So I would like to emphasize that this is not magic, and it's strictly not a prediction, because you did something, you imposed norm preservation to get that particular nonlinear martingale structure without which we won't get the point. So I think maybe Angel will talk more about it. In some sense, the Born rule has been filled in. What is important? The important message is that there are fluctuations. These fluctuations around an equilibrium is a source which can solve the measurement problem. But then there are many caveats which have gone. We don't predict GRW, but GRW can be contained as a special case in trace time. Okay, so I'm done with the maths. We are open for discussion. We'll have about 20 minutes. All right. So what did we achieve? You can go back. I don't want to go back all the slides. There was motivations for saying that quantum theory is incomplete. What all did we manage to solve? Canonical quantization is emergent. Tick. Yeah, that's a good thing. Potential resolution of the measurement problem. I don't know what spelling I have written here. Potential resolution of the measurement problem. Half tick. Yeah, you decide. Underlying dynamics is non-local. There's the issue of non-locality. So let's discuss this a bit. This is a very interesting point. Let's look at the level of the average, the thermodynamic theory. If you had replaced C tilde by its average, there are no fluctuations. You got ordinary quantum field theory, which has, as Angelo mentioned, it has micro causality. But we also know that the theory is, quantum theory is non-local. But in the sense that when collapse happens, there is some kind of a non-local influence. But it's puzzling in quantum theory. It's not puzzling here because, in the present context, because when you add these stochastic fluctuations to C tilde, you get a Schrodinger equation. It doesn't matter if it is linear or you get a Schrodinger equation which has fluctuation terms. Okay? And then when we come nonlinear, still there are fluctuating terms which are nonlinear. These will cause non-local influences, but there is no signaling because of the particular structure. The density mass equation of the density matrix is linear. Yet there is scope in this equation for non-locality because of these fluctuating terms that are present in the non-linear, which is not a feature of the Schrodinger equation. So in that sense, we have a certain kind of explanation for Bell non-locality. You can debate that with me. Cosmological constant, question mark. Adler has some claims, some ideas. There is a story behind this cosmological constant problem. If supersymmetry is exact, then the zero-point energy coming from bosons and fermions cancels exactly, and the cosmological constant is zero. Unfortunately, exact supersymmetry won't work because it doesn't give you the desired particle spectrum. Similarly, if you have a scale invariant theory and the scale invariance is exact, the cosmological constant is zero. But again, that is, you don't have exact scale invariance in nature. You won't give you the right particle physics. So there are some ideas in trace dynamics which I don't fully understand, neither are they fully developed, which may be useful in studying the cosmological constant problem. You can look at that. Okay, what about gravity and unification? If quantum theory is an emergent theory, we should not quantize gravity. You don't use emergent phenomena in a fundamental way. The quantum theory is no longer fundamental. It works for other interactions, that is true. But since it doesn't seem to work for gravity, one possibility is that to not think of using an emergent phenomenon in a fundamental way. Rather, maybe there's an underlying theory from which both quantum theory as well as gravity are emergent. Someone was talking about emergent gravity. So there are emergent gravity models with emergent quantum theory. Maybe need to unify their underlying theories. Okay, so now I will just list what I think the outstanding problems of trace dynamics, more to be done. Why should the norm be preserved? I already talked about it. How to uniquely predict a model like GRW or CSL. There was the issue of the preferred frame, because that is how you, if you want equilibrium with the thermal reservoir, you need a preferred frame. And which is that frame? Lorentz invariance is broken in between the finally recovered. How to test trace dynamics in the lab. Maybe collapse models are a test for trace dynamics. Can one make collapse models relativistic? Here there is a very interesting take in trace dynamics which seems to suggest that you will not be able to make relativistic collapse models. And the reason for that is that when you add fluctuations to C tilde, statistical fluctuations is the Adler-Miller charge, if you want, that's a matter of detail, the canonical averages to be still convergent in a mathematical sense, despite including fluctuations, you need to retain this term e to the minus tau h. We dropped this term, we came to a much lower energy scale, but for this formal reason you have to keep it, and the moment you do that, you are breaking Lorentz invariance. So, the message here seems to be that when you include these fluctuations to make a non-relativistic collapse model, you will not be able to generalize it to a relativistic case if the trace dynamics approach is correct. Okay. And then this assumption that there is no preferred quantum state in the ensemble. Okay. Which is how we could get the Planck constant out of the theory. Why is that assumption there? And trace dynamics is a formalism. It's not a particular theory. No specific matrix model was given. Namely, the actual form of the Hamiltonian was never prescribed or derived in any fundamental sense. And the next point is something I didn't really talk about. You know, this is I effective has a I and a minus I. They come in pairs. We have kept only the I. We threw away the minus I. And you get quantum theory with the correct commutation relation if you keep the I. You get a different world, so-called a shadow universe, if instead of I, you keep the minus I. And there have been some speculations you asked about it, whether dark matter and dark energy are actually this shadow universe of trace dynamics. It is very, very speculative. It needs more work. Where does the thermal reservoir come from? The whole universe is trace dynamics. Where is it's a box of gas, this box of matrices. The whole universe is that. So what is it in thermal equilibrium? How to include gravity? Adler has reasoned that you cannot convert the gravitational field into matrix variables, essentially because if you were to write down the Lagrangian in a curved space, you'll read a root minus g in the Lagrangian. And if you raise that g, g is a field, of course, so all the components would have to be further raised to a matrix status, and that messes up with the structure of trace dynamics. So it's not clear how to do that. Okay. The last point, which Adler doesn't discuss, but for me it's very important. There is a classical space-time structure, Minkowski space-time, underlying trace dynamics, which was always taken as a given that there's a Minkowski space-time. But that is classical, and in this diagram I show something I mentioned as a comment in an earlier talk, that that's a problem which makes quantum theory unsatisfactory. This time evolution is part of a classical space-time which is produced by classical bodies. These are a limiting case of the Schrodinger equation. So you see there's a circle, there's a self-reference which is not very satisfactory. So if you are using trace dynamics with a given space-time to derive the Schrodinger equation, you still don't get out of this loop. You take a classical background as given, which should not be the case. Suppose the entire universe has no classical bodies. There won't be a classical space-time, and yet I should be able to do quantum mechanics. So there should be a quantum theory without classical time, such a formulation. Similarly, I think there should be a formulation of trace dynamics without classical time. So we have been doing some work on that, not fully successful, but still ongoing stuff. So I think that is all that I have to say. We can either close early or we can discuss. Maximum number of questions?
2.
No, maybe you can keep on asking unless someone else has. If someone else has a question, then 1, and then we go around.
Okay. So the first question is regarding the collapse.
Go back.
Yeah.
First question was, how many questions can I ask?
Okay.
Slide.
No, I mean that T tends to infinity collapse. Yeah. After that, this.
Next slide.
Yeah. So here the probability matches with the Born's rule at T tends to infinity. So there is no reference to measurement, right?
Yes, there is no reference to measurement. This spontaneous collapse.
Okay, so I mean.
Now you're asking how to solve the measurement problem.
Yes.
Okay, that is. Yes, Angela will do that. In my context, that means the following. If you look at the last equation, there is a reduction rate. You know what physicists mean by infinity is larger than some time. So I'm giving you a reduction rate which is 1/4 beta r square V0. You can see that, no? So any times larger than that are infinite. So long as you can define a collapse rate, which he'll do much better than me.
And the thing is that...
Should we go around? Are there any other questions? Okay, we'll come back to you. Yeah.
Because
what's the difference?
Like in thermodynamics,
maybe it's just my ignorance. So just tell me, what's the difference between static equilibrium and dynamic?
like in a statistical ensemble, our macro variables, those are fixed.
Yeah. In that, are those macro variables also changing?
No, hence that's why it is.
Yeah.
Variables are.
Yes.
So.
No, this is done. Okay, let's go back to that. So this is all normal equilibrium or dynamic equilibrium. You agree, no?
Static or dynamic?
But static, like if your atoms are not moving, that's static. That's not good equilibrium. Like normal equilibrium is all dynamic. So let's go back to that slide. Yeah, so what I was saying, I mean, I don't know if I have a fully satisfactory answer. If you look at the first equation, put W equals H, the way it is written, it is equilibrium. There's no time evolution. That is correct. There's no time evolution. But I just use this trick that last term from trace dynamics, I know that is the trace dynamics time evolution equation. I just said that equals x dot. So it's as if the equilibrium situation contains information about the dynamics. I should come with a better answer. I don't, but I have not found a better answer. Looks puzzling, of course. You are at equilibrium and you got out a time-dependent equation. It's not that the canonical average of XU will not be evolving. That is true. But if it were evolving, this is how it will. I have to think. I have not come.